Hey everybody, how are we doing? It's alright. Still just kind of getting things back into the groove here. With the daylight savings time and the long weekend and, the decent weather coming in got everybody feeling a little itchy and antsy, I'm sure. All right. Last time we had spent some time in class talking about the key features for these rational functions and kind of how to find them. And I think I assigned the problems 1 through 12. Are there any questions you guys had about 1 through 12? Okay. I am also going to assign today, in addition to doing new stuff, I'm gonna assign 13 through 24. We're going to be looking at how you can take those key features and turn them into a graph, use them to sketch a picture of a graph. So I'm just going to do a couple of example problems from this set to kind of illustrate how to do that. Does anybody have a favorite number between 13 and 24? 20, somebody said. Let's take 20. That sounds as good as anything. Okay. It was the loudest one. There's no favorites there. All right. So 20. First thing I would want to do to start this problem would be to starts with an F. Factor. So if I look at this, oh no, you guys picked a good one, right? What do you see that's makes this a little inconvenient? Anybody? What do you notice about this problem that makes the factoring a little inconvenient?
There's coefficients in front of the leading.
Yeah, excellent. So there's a leading coefficient that's not 1 on these, which means that we're going to have to do that long factoring. So we need to find the two numbers that multiply to give us 3 times -4 or -12, and then add to give us -1. What are those two numbers? -4 and 3, right? Oh, they're just like staring right at us. So remember, those two numbers, though, don't tell us how to factor. What they tell us is how to break up that middle term. So I'm going to break that up into -4x plus 3x, and then make two groups. From the first group, we can take out a greatest common factor of x. From the second group, there is no greatest common factor, but we can always take out a 1. So we take out a 1. And then each of these factors now contains a 3x minus 4. So when I factor that out, I'm left with an x plus 1. So that's the numerator factored. Woo! There's a little bit of a workout there for 9:21 on a sunny Tuesday morning. And then, unfortunately, it looks like we're going to be doing the same thing now for the other one, for the denominator. Oh my goodness, are we okay? That sounded like some serious hacking. All right. Multiplies to give us -8 and adds to give us +7. What do we got there? No. 8 and negative 1. Yes, very good. Again, this is the kind of thing that you should be able to do like inside of 10 seconds. Find those two numbers that do that kind of thing. So again, at 8 and negative 1, just tell us how to break up that middle term. Make our two groups. From the first group, we can take out a 2x. From the second group, I notice, hey, I have negative x minus 4 instead of x plus 4, so let's take out a negative 1. Both of those then contain an x plus 4. So when I factor the x plus 4 off, I'm left with 2x minus 1. So my problem really, the factored version, would look like this. And before we get going into the problem, I should check to see if there's any reducing that can happen. Is there anything that can reduce here? No way, Jose, right? Each factor is unique. All right, so let's start by finding the vertical asymptotes. How do I do that? These are things that you would need to know for any kind of future homework quiz. It would be like how to find these key features. Not saying that that could be happening later this week, but I don't know, maybe. We set the denominator equal to 0. So when I do that, I get negative 4 and positive 1/2. Everybody feel okay there? Then we'll find our x-intercepts. How do I find the x-intercepts? Numerator equal to 0. That's correct. So that's going to give me 4/3 and then negative 1. But remember that we agreed that we were going to write these as points so as not to confuse them with our vertical asymptotes. Then maybe I'll find the y-intercept. How do I find a y-intercept? Plug 0 in for x. So that's going to give me 1 there, right? Negative 4 over negative 4. Yeah. And again, I'm going to write that as a point so as I don't confuse it with like a horizontal asymptote or something. And then we need our horizontal or slant asymptotes. How can I tell the difference between if it's going to be a horizontal asymptote or a slant asymptote? What do I need to look at? The degree. The degree for the numerator is 2, and the degree for the denominator is 2. Since they're equal, I know it's going to be the leading coefficient of the numerator over the leading coefficient of the denominator. Well, it's also, I know it's going to be a horizontal asymptote. Should say that too. The leading coefficient of the numerator, right? It's 3x squared stuff. And then over 2, the leading coefficient of the denominator, it's 2x squared and then stuff. Good with that, Colbs? Yeah. Okay. All right. I'm going to start sketching in the graph because rather than doing the end behavior first, because sometimes I don't even need the end behavior or all of the end behaviors. So if I don't have to find them, you know, like I'm good with just like not doing it if I don't need to. So 1, 2, 3, 4. So there's x equals negative 4. And then x equals positive 1/2. Okay. 4/3, comma 0, and then -1, comma 0, and then 0, 1, and then y equals 3/2. Is everybody okay with how I plotted that stuff in there? Josh?
Where are you like plotting it on the computer? You can't see it on the
It just might not have caught up.
oh,
So sometimes the syncing is
oh,
just,
that's there now.
yeah, it just takes it lags or whatever.
Okay.
But it'll dump in there eventually. I pushed this, forced to sync there to get it to catch up for you. Yep. Okay. So if I look now, I can tell that I know how to draw this section of the graph and this section of the graph based on just the asymptotes that are there and the points that I have to pass through, right? So on the far right section, I know I have to start at the asymptote. And because I know I can't pass the horizontal, I know it's got to look like that I can't start up high because I would have to pass the horizontal to go down to it. And my end behavior at the very, as x goes to positive infinity needs to follow that horizontal asymptote, right? That's the only way to fit that in there. Is everybody cool with how I was able to surmise that just by looking at the points? If I look at the middle section, I know that if I have to go through these 2 points here, it's probably got to look like that, right? And now, Mr. Kulik, you're passing through the horizontal asymptote there. Yeah, but it's not at the end of the graph. So the horizontal asymptote you can kind of jump through if you need to in like a middle part of the graph like we just did. What you can't cross is, out at the end. Now, this last section, I don't know if my graph is going to be up here or down here. That is unclear, right? Because I have no points over there to figure that out. So what I'm going to do is I'm going to look at my end behavior as x approaches -4 from the left. So if I plug in something a little less than -4, I'm going to think about what I get inside of each of these factors. So that's going to be a negative, a negative, a negative, and a negative. Is everybody okay if I pick something a little less than -4? All those quantities are going to be negative. So what kind of number am I going to get there? Well, what's negative times negative? Positive. So you have positive over positive, which means it's going to be positive number, right? So it tells me the end behavior is going to be up here. Is that okay with you guys? I didn't actually plug anything in because, well, if I don't have to use my calculator, I don't really, you could if you wanted to. But if I know that it's going up there and it has to follow, can't cross the horizontal asymptote again, I'm good. So I just checked for that piece. It was the only piece that I really needed the end behavior for. So rather than calculating, all 6 of those end behaviors, I'm going to plot what I have and see if I can just okay, I really only need to find one of the 6. Boy, that seems like a much better deal to me than finding all 6 of them. What do you guys think on that? You want to do one more? I see some head shakings. No one seems that excited, though. Who's got another favorite number other than 20 between 13 and 24? 16. Great. Let's do it. So again, what do we want to start with by doing? Factoring. Now this one should be pretty easy to factor. The numerator is just a difference of 2 squares. The denominator, if I take out a greatest common factor of x, the two things that multiply to give me -8 and add to give me -2 are -4 and +2. Everybody feel good? So I have, I factored this. Any reducing that can happen? Nope. So it tells me there's no hole, right? If there's no reducing, I can't have a hole. So for vertical asymptotes, again, I'll set the denominator equal to 0. I get 3 vertical asymptotes. Oh, dear me. Is everybody okay with me just writing down the vertical asymptotes here and just saying we set the denominator equal to 0? I wrote down more work on the last example. I'm just going to kind of be a little bit briefer here since we already talked through the other one in, I think, a pretty good amount of detail. And that should be something that realistically at this stage of the game we can do in our head, right? If we have a factored form and that we're solving by just setting it equal to 0, we can probably do those in our head. To find the x-intercept, we set the numerator equal to 0, so we'll get 1, 0, and then -1, 0. Everybody feel good there? Nothing too tricky. If I plug 0 in for x, what's going to happen? Right? If I try to find the y-intercept and I plug 0 in for x, is there going to be an answer? No.
Just cancel
No, I'll get like 0 over 0 or
out.
something.
Yeah, right.
Or like something over 0.
Yeah.
So there is no y-intercept because I have a vertical asymptote where x equals 0, right? So I can't have a y-intercept because the graph can't cross a vertical asymptote. Everybody's good there? If you plugged it in, you would have just gotten an error on your calculator if you tried to type it in. That's okay. Probably just means you're trying to, or plugged in something where you have a discontinuity. And then the last one is the horizontal or slant asymptote. So we need to look at the degrees. The degree of the numerator is 2. The degree of the denominator is
3.
Since 2 is less than 3, we have a horizontal asymptote, and it's always y equals 0 if the numerator degree is less than the denominator degree. Is everybody cool? Degree is the biggest exponent, right? All right.
Yeah, how did you find the degree then?
It's the biggest exponent on the variables. So in the numerator, the biggest exponent's a 2, and the denominator is a 3, because it's x squared is the biggest one, and then x cubed. Cool? All right. Let's go ahead and sketch in a picture here. Try to draw a little straighter of a line. I think there's a ruler function on this, but I always forget to try to use it. Let's see, we have -2. We have 0. And then +4. We have 1 and -1. And then we have y equals 0 as our horizontal. This is a bummer, guys, because I can't tell. We have like 4 sections of graph that we have to fill in, right? Looking at the points, I can't tell anything going on there on which of the ways it's going. So I'm going to need to look at least a bunch of these end behaviors. So we'll just start on the left. So we'll go look at -2 from the left-hand side. If I plug in something a little less than -2, negative, 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 and negative. 5 negatives means it's negative. So I know that this piece is going to look like that. That's telling me this, right? So if I do the same thing, but I'm going to take just something a little bit bigger than -2, the only thing's going to change is that one, right? Is now going to be positive number, because if I have like -1.99, so that means it's going to go to positive. So this is going to go like this, and I guess it's got to keep going down, right? It seems unlikely that it would double back up there. If I really wanted to, I could check it though. You know, just look at something a little smaller than 0. So that's negative, that's positive. That one would be positive, that one would still be negative. So yes, indeed, that one's going down. If I look at the other side of 0, the only thing that changes is that one changes from negative to positive. So this one then would be going up now. So it's going to go down through this, and I'm guessing continue going down, but we'll check that here in a second. So x approaches 4 from the left. So that's positive, that one's negative, positive, that'll be positive now, that's positive, yup, that one's going down. And then our last one, 4 from the right, the only thing that changes is that becomes positive now. So we'll be up at the top. And there we go. So that's kind of the gist of what we're doing here. Should look fairly similar to what you did in the last Delta math, where you had to put in the key features and then you just hit plot, and the computer built something that passed through everything for you, which is fine. It's basically doing the same thing that we're doing here. It's just like, you know, like figured out the end behaviors and then drew in to pass through the other stuff. What do you guys think on this? It's okay. Basically the same thing as yesterday, but you have to like build a little picture out of it at the end. But all I'm doing the exact same skills that I did yesterday. I'm just taking the numeric result and building a picture out of it, right? But there's no new conceptual piece that happened here. What do you think? Sound good? Feel okay? All right. And again, if we were to have a homework quiz later this week, you'd have to be able to find things like vertical asymptotes and x-intercepts and, you know, those key features, domains, stuff like that. You know what I mean, guys? All right. Today, the other part that we're going to talk about today is solving rational functions or rational equations. So there's lots of different techniques you can use depending on the situation. I'm just going to teach one technique that's the most versatile technique. It can be used in every situation, and it's never never really a inconvenient one, like it doesn't get too gross ever. Rather than having a bunch of different techniques that you might use depending on the situation, I'm just going to give you the most versatile one that works in any situation and really never gets too bad. Everybody's cool with that? So the idea here, what we're going to use is called clearing fractions. So to clear fractions, what we do is we multiply both sides of our equation by the least common multiple of the denominators. So if I look at this, I really have three denominators, right? Well, two of them are the same. So really I'm just considering the least common multiple of x and 1. What's the least common multiple of x and 1? That's incorrect. Let's talk about what a least common multiple is. So to find the least common multiple of two numbers, or two things, we need So to find the least common multiple of A and B, that least common multiple is going to contain each distinct prime factor of A and B. And then the power on each prime factor is going to be the largest power of that factor from either A or B. So for example, let's just do some number ones. The least common multiple of 2 and 4 is... It is not 2. So the prime factorization of 2 is 2 to the first. The prime factorization of 4 is 2 squared. There's one distinct prime between 2 and 4. That's the number 2. The biggest power on 2 between 2 and 4 is the second. So my least common multiple is 2 to the second, or 4. Least common multiple of, say, let's say 4 and 6. Well, the prime factorization of 4 is 2 squared. The prime factorization of 6 is 2 to the first times 3 to the first. So my least common multiple contains the factors 2 and 3, the distinct primes. The power of 2 should be to the second, because that's the biggest power of 2. The power on 3 should be to the first, because that's the biggest power of 3. So the least common multiple of 4 and 6 is 12. Let's do one more, yeah? Okay. The least common multiple of, let's say, 24 and 18. The prime factorization of 24 is 2 to the third times 3. The prime factorization of 18 is 2 times 3 squared. So my least common multiple contains the factors 2 and 3. The power of 2 should be to the third. Good. And the power of 3 should be to the second. Very good. So that comes out to be 72. What do you guys think? Feels okay? So if we go back and we want the least common multiple of 1 and x, well, the prime factorization of 1 is 1. The prime factorization of x, how do I factor a polynomial? Oh, I just factor it, right? Can I do any factoring to x? No, man, it's just x. So my least common multiple contains the factors 1 to the first and x to the first, or just x. Oh, okay, well that seems fine. So how do you guys feel on that? So if we go back to our example then, we'll multiply both sides of the equation by x. So when I distribute the x through x times x is x squared. What do I get when I do x times 3 over x? Right, so I think about it as a fraction. So I multiply the tops together. So I'd have 3 times x over 1 times x. So the x's would cancel out, leaving me with just 3 to the first. And then I multiply x times 4, and that's just going to be 4x. So far, so good. What type of an equation are we left with? Polynomial, but more specifically, you'd say it's what type of polynomial? What's called quadratic. Usually we taught by degree is usually the primary classification for polynomials. Trinomial is not incorrect, but more specifically than that, we'd say it's quadratic. How do we solve a quadratic? Well, not just the x's. You want to get everything on one side so it's equal to 0, right? And then we could either, what are some of the ways we might solve this? Quadratic formula, or I probably wouldn't go that route. That's a little bit, it's like using a sledgehammer to pound a nail in. How about just factoring, right? That's probably your primary 2 would be the quadratic formula or factoring. Everybody feel okay there? For this one, which one would probably be faster? Factoring. Why? The leading coefficient is 1, so if it's factorable, it can be factored really quickly by just finding the two numbers that multiply to give me -3 and add, or +3 and add to give me -4. What are those two numbers?
4 and -1.
So how about -3 and -1? Right? Ay, guys.
I said it.
You said it. Okay. It was quietly. That's why I missed it. So the two solutions I get are 3 and -1. Everybody feel okay there? We're not done though, because the equation we actually solved was polynomial. The domain for a polynomial is always all real numbers. The equation we wanted to solve for was a rational equation. The domain for a rational function could have restrictions in it. It could have values that are missing. What we need to do is we need to check these values to make sure that the solutions 3 and 1 are not one of the values that might be missing from the domain of our rational function. Now, this is a very easy check to do. All we need to do is we need to take our solution and plug it into each denominator in the original and see if I get 0. When I plug 3 into x, does that make 0? No, man, it makes 3, right? When I plug 1 in for x, does that make 0? No, man, it makes 1. So guess what? Both these solutions are fine. They check out. Now, the check is super easy. What's going to be the hardest part about the check? Remembering to do it. Okay, remembering to do it. If one or more of the solutions fail, we can just discard those solutions. We call solutions that fail our check extraneous solutions. I'll write down that word here in a minute when we get an example where that happens. All right. New example. Solve the equation. The technique we're going to use is called clearing fractions. So what we need to do is we need to multiply both sides of the equation by the least common multiple of like 1 and x plus 1. The prime factorization of 1 is just 1, man, like, and no big deal there. The prime factorization of x plus 1, can I factor x plus 1? No, man, right? Like, there's nothing to factor with that. So just x plus 1, so my answer is just 1 times x plus 1, or just x plus 1, right? So we'll multiply both sides of our equation by x plus 1. So if I multiply the x plus 1 times x, I'm just going to write it as x times x plus 1 for now. We can distribute things out later. Then if I multiply x plus 1 times 6 over x plus 1, remember this is like multiplying fractions, so we multiply the tops together. We multiply the bottoms together. And then that can reduce down, right? Where I'm going to stop showing the reducing here on the next example, though. We're just going to do the reducing in our head. Is everybody okay with that plan? Because that's really where we should be at this stage of the game. So we're there. Let's distribute the x through, I guess, if we're going to have to solve for x here. So I'm left with x squared plus x minus 6 equal to 0. What type of equation is this? Quadratic. How do you want to solve it? I would factor it too. What multiplies to give us negative 6 and adds to give us positive 1?
3 and negative 2.
3 and negative 2. Everybody good? So my two solutions are negative 3 and positive 2. Am I done? No, what do I still have to do? Gotta check. Where do I check at? The very beginning. If I plug negative 2 into x plus 1, does that make 0? No. If I plug positive 2 into x plus 1, does that make 0? No. Guess what that tells me? Both these solutions work. I think I might have said minus 2 when I meant minus 3. Did I say that? Okay, my mistake. I realize that it's a little, right now, it's not what I meant to say. All right. I think I have 2 more examples and we'll be done. How's that sound?
Amazing.
Yeah, right? I'm pretty good with it. It's a good amount of work we've done today. All right, let's look at the next one. Ooh, scary. Mr. Kulik, that just got a whole lot more complicated. I'm not with this. It's fine, it doesn't really matter. All right, they're all the same. All right. So, first thing I would do is, nah, don't need to do that. Yeah, and to find the least common multiple, I want things in factored form. That just makes it easier. So to find that least common multiple, I'm going to start by factoring the x squared minus 4x plus 3. So x minus 1, no factoring needed there. X minus 3, no factoring that can happen there. X squared minus 4x plus 3, well, the factoring of that is x minus 3 times x minus 1. So my answer, or my least common multiple, has a factor of x minus 3 in it, and a factor of x minus 1 in it. And the biggest power of x minus 1 is to the first. And the biggest power of x minus 3 is to the first. So that's my least common multiple there. Everybody feel okay with what I did there? I'm writing out all this least common multiple stuff. You don't actually need to do this on your paper if you can see them in your head. But we felt in the beginning like the least common multiple is not obvious for us, so I been wanting to write them out. So if you go back and look at it, you're cued again to what we were doing here. So I'm going to multiply both sides by x minus 3 times x minus 1. I always leave the stuff in the factored form like that. It just makes life a little bit easier. All right. Let's try to write our answer without having to show the reducing on this one. So when I multiply the x minus 3 times x minus 1 to 2x over x minus 1, what is going to cancel? The x minus 1s. Everybody see that? What's going to be left over then? 2x times x minus 3. Everybody good with that? Okay. If I multiply the x minus 3 times x minus 1 to 1 over x minus 3, what's going to cancel? The x minus 3's. What's left? The 1 times x minus 1. Now, do I have to write the 1 there? No, but I'm going to write it there just so you're used to like numerator and then whatever's left over from the least common multiple. And then when I multiply x minus 3 times x minus 1 to 2 over x squared minus 4x plus 3, remember that x squared minus 4x plus 3 is really x minus 3 times x minus 1. What's going to cancel? Yeah, so what are we going to be left with? Just the 2. How's this look so far? Pretty good. So we'll just distribute things through. We're left with a quadratic. I'm going to combine like terms and move everything onto one side. I'm going to do that all in one step. Everybody okay with me processing that in one step? combining like terms and getting it equal to 0. To solve 2x squared minus 5x minus 3, what method should I use? What did you say? I just literally couldn't understand what you said.
Factory?
You could, right? Do you know that this one factors? Because the leading coefficient is 2. Is it going to factor quickly, or is it going to be the longer method? It's the longer method. If it's me, anytime I see a leading coefficient that's not 1, that I can't turn into 1 easily by just like dividing by some constant, I'm going to just use the quadratic formula. Because most of these ones where there's a leading coefficient, I can't tell if it factors or not, but I know the quadratic formula always works. So I would just do that here, but this one does factor and that would work, and it's fine to do that, Colby. I would just choose to not to. You know what I'm saying? Because it's probably going to be the same amount of time either way. And with the quadratic formula, I am guaranteed an answer. So I have negative b plus or minus the square root of b squared minus 4ac all over 2 times a. Negative 5 squared is 25. 4 times 2 times negative 3 is negative 24. 25 minus a negative 24 is 49. The square root of 49 is 7. 5 plus 7 over 4 is 12 over 4, which is just 3. 5 minus 7 is negative 2 over 4, which is negative 1/2. So I have x equals 3, and then x equals negative 1/2. Am I done? No, what do I still have to do? Check it. So if I go and I take my x equals 3, I plug it into x minus 1, do I get a 0 denominator? If I plug it into x minus 3, do I get a 0 denominator? Yes, right? 3 minus 3 is 0. At that point, I'm going to stop. This one is gone. We call this an extraneous solution. It does not count. Okay, as soon as I get 1 0 denominator, that's enough. All it needs to happen is once. Now I'll check my x equals negative 1. If I plug x equals negative 1/2 into x minus 1, that's fine. If I plug in x minus 3, that's fine. If I plug in x minus 3, that's fine. If I plug in x minus 1, that's fine. So that solution works. So this problem has just one solution, x equals negative 1/2. Yes, Colby?
You only plug it into the denominator?
Correct. I only care about if I get a 0 in the denominator. That is correct. When I'm checking, I only care about the denominators. I have one more example for you guys, and we are Audi 5000. Sound good? Mm-hmm. What do you guys think? Pretty good deal? This is an efficient use of class time today, Mr. Kulik. I like it. Under an hour. Yeah, man, I'm aimed to please here. All right. So, I would start the same way. I'm going to begin by factoring everything I can. The only thing that needs factoring is that last denominator, and in fact, that's a factoring problem we've done before. It's the exact same factoring problem we saw. What will the least common multiple here be? Good, x minus 1 times x minus 3, or you could write as x minus 3 times x minus 1. That's okay too. They mean the same thing, right? Multiplication is commutative. So I'll multiply that to both sides of our equation. When I multiply that to the first fraction, the x minus 3's are going to cancel, leave me with 2.5 times x minus 1. When I multiply to the second fraction, the x minus 1's are going to cancel, leaving me with 0.5 times x minus 3. When I multiply to the third fraction, both the x minus 3 and the x minus 1 are going to cancel, leaving me with just x squared. Now, I don't love the decimals here, but if I look closely, it looks like when I combine like terms, I'm going to get rid of them. So I'm not going to worry about them right now. If after I distribute things through and do my combining, if I still have decimals, I will worry about it then, but I don't think that's going to be a problem for me. So what do I have? I have 3x minus 4. Fantastic, no decimals, right? If I did, I might multiply both sides by 2 to get rid of any kind of decimal in there, but it doesn't even really matter. You could hang the decimal on if you're just going to use the quadratic formula anyway. But I'm left with a quadratic again. I'm going to get it equal to 0. This time I'm going to subtract everything to the right-hand side, or add, because I want that x squared to have a leading coefficient of 1 and not negative 1, because it makes the factoring easier. Although if you did it the other way and used the quadratic formula, that's okay too. So here I get okay, so multiply, it gives me negative 4 and positive 1, right? Oh no, that gives me nothing, right? Those don't work. That's not factorable. Oh no! What do I do? Yeah, I got to use the quadratic formula. Oh, brother. That's okay. Let's see. Negative 3 squared is 9. 9 minus, and then 4 times 1 times 4, 16. 9 minus 16 is negative 7. Uh-oh, Raggy, what's that mean? I get an I. So what would I say here? No real solutions. Wah, wah. You know, if they wanted complex solutions, this answer still counts, but like it ain't real, so typically when we talk about rational functions, we'd only be asking for real solutions. What do you guys think? It's okay? Well, let's be done here for today then. So for your homework set, we're going to have 13 through 24. That's like 14.1 questions. And then based on the new stuff we did today would be 25 to 32. That's like our 14.2 questions. Everybody feel cool? Alrighty then, folks. I'm going to be done. We did it inside of an hour. That's a good day, right? Why don't you guys take the remaining 20 or 25 minutes here and kind of get cracking on the new homeworks, or if you have old stuff that you're still kind of plugging away at, you could take a run at that stuff. Or if your Delta Math still isn't finished because you're like, ooh, I don't know how to do the graphing part or something, you know, like you could finish that up instead. Reminder, if you finish any late work, you need to email me to let me know to check it, because like the Delta Math stuff, I don't get any notifications from Delta Math if you do more.